you. Good morning. Good morning, everyone. Welcome to our monthly webinar for Opencloudification. My name is Luca Gattubiggio. I'm the Innovation Manager at ELSEC. And today we're going to talk about remote attestation with our colleague here, Jordi. Jordi, I'll give you the floor later. First, a short introduction on ELSEC. ELSEC is, as we call ourselves, a digital cybersecurity catalyst. Our main goal is to promote innovation and facilitate other companies in improving their cybersecurity and their cybersecurity solutions. And we do this following and providing support in a lot of different topic and domains. In this specific case would be cloud, but not necessarily relegated to cybersecurity. We tend to extend this on as a full support on the domain that we're following. So in this case, Opencloudification focuses on the open cloud technologies that can be used for cloud. But of course, cybersecurity is an important part of it. Our main website is opencloudification.com. There you can find all the information related to the project, the partners, but also a lot of interesting content that might be useful for your company. Either if you're interested or you would like to join the cloud for the first time, or if you're already an expert on the topic and you would like to do the next steps in terms of improvement using cloud and cloud technologies, together with evaluating potential alternatives, doing some research for cloud and edge solutions. This is a joint effort of ELSEC as the coordinator of the project, together with IMEC and ID Lab, which are our technical partners from Ghent, and the Beacon as our reach out to the companies from Antwerp. The idea behind Opencloudification, as an example, is the fact that the open cloud technologies are plenty, and especially if you're not familiar with this type of technologies, it might be challenging to getting started, for example. And this is why we are here to offer you some guidance and support on sharing and proposing some potential technologies that might be of your interest. But Opencloudification is not only offering guidance. We have events, we organize workshops. The webinar is just a little part of it. So make sure to reach out and be aware of all the activities that we organize. Again, there's a section on our website in which you can find all this information on opencloudification.com. A brief description on a couple of additional projects that we as ELSEC have at European level. So the first one that I would like to introduce is KISME. At kisme.eu, you can find all the information. Here we're trying to offer services and support small and medium enterprises with their cybersecurity. So please do reach out if you think that your company might need a hand in terms of cybersecurity. And at the same time, there's a second project which is called KISD. So similar name, but different target. In this case, we can offer support to companies that can do pen testing activity and vulnerability assessment up to 200,000 euros. The open call will be open very soon, before the end of 2024. So go check kisd.eu if you think that you can provide some services. We are happy to help. And with this, I'll stop to share my screen, and I'll give the floor to Jordi, which is here with us today, talking about remote attestation. Jordi, the floor is yours.
Thank you. I'm going to set up my slides and share my screen.
Yeah, perfect.
Are you seeing the correct screen? Yeah, right?
Yes, yes.
Okay. So good morning, everyone. My name is Jordy. I work for Ghent University and IMAC, but I'll get to my introduction a little later in a few slides. Today, I'm going to talk about trust and attestation, and I sort of want to provide an introduction to the general topics that you need to talk when you want to talk about remote attestation. And I'm going to look at a few applications, but more on that later. I'm going to start with sort of a few use cases. Well, everyone probably knows our three big friends who own like 70% of the cloud computing world or something. And a lot of companies use them for data storage, for computing power. And they just send their stuff there and hope that everything runs securely. But there's a few questions that you need to ask, and some of them might be pretty easy, but some of them are a bit more difficult. Like, do you trust the company? I mean, yeah, probably. Like the chance that Google is going to try and like actually want to steal your data is like pretty small. But then, do you trust all of their processes? Do you trust that like nothing can happen to your data? And do you trust their employees who might have access to it? Like, do you trust all of them to not do anything wrong? And I think an important one in certain sectors, especially like medical sectors, is like, are you even allowed to just send data there and trust them? You know, there might be rules on like who can see it and what risks you can take and what risks you cannot take. So this is like one of the main use cases also of remote attestation. It's verifying these remote assets. So remote attestation, basically in one line, verify the integrity of remote systems. Any system that you do not have like securely in your own data center, you should verify the integrity of it. And there's many more use cases, right? Like confidential AI. If you have a model running somewhere and you want to feed data into it, but you want to make sure that that the model will not leak your data or that no one can steal your data, you're going to need to do some sort of remote attestation on whatever is running that model to make sure that doesn't happen. Linked to trusted computing, you need to verify the trusted computing instances to actually be able to use them properly. And then we have like critical infrastructure, autonomous vehicles. You know, you can keep going with these examples. Anytime you have any sort of compute that is outside of your direct control, you need remote attestation to sort of verify its identity. Now, what are we going to talk about in this webinar? The first part of it is going to be me just covering remote attestation. There's a few topics, a few like terminologies and things that you need to understand if you want to have conversations about remote attestation. So I'm going to start with a quick overview of all of that. And then I'm going to sort of boil that all down into three major questions. If you don't get the questions yet right now, that's fine. I'll introduce them while I'm explaining everything else. But what we want to answer is like, what do you measure? What are your references and how do you make a decision? And these questions are going to come back throughout this webinar. And I'm going to try and apply them as well to two major technologies. Mainly, I'm going to talk about like TPM-based attestation and then trusted execution environments, attestation of those, specifically Intel SGX for this presentation. So that's sort of what I'm going to talk about today. Now, who am I? I am a pre-doctoral researcher or a PhD student, but I find that the first word sounds a bit nicer. At Ghent University in IMAC. My research focuses on mainly like trusted edge computing, but there's also a bit of like confidential computing and trusted computing in there. And on top of that, I do some teaching every now and then with some programming courses and security labs. My LinkedIn is right there, and there's like a little picture of me if you want to connect or something. But yeah, let's get into it. I'm still like a little bit sick, so if I have like a little cough every now and then, excuse me. The remote attestation procedure. I like to make the analogy, and it's not just me, it's like also in some sort of standard this analogy, with sort of traveling. If you travel abroad, there's a foreign government that needs to trust you. They need to let you into the country. But they don't know who you are. You just show up and they have no evidence on you. Now, we've come up with a really great solution to that. Your local government will give you a passport, which basically certifies that the information in it is valid and it identifies you to the foreign government. And if you're lucky, like me, and you have a European passport, then there is going to be some sort of trust relationship between that foreign government and your local government, which allows you to like easily get into the country. Now, if we translate that in like to a fun diagram, it looks like this. So the traveler needs to provide some proof of identity to the local government, which then certifies that information with a passport that is trusted by the immigration of wherever you want to go. Now, if you kind of look at sort of a passport, you can easily translate that in like computer science terms, sort of as a certificate, right? It's basically a signed certificate by a trusted entity, your local government, that another entity can use to trust you. And then I now like to translate all of that into remote attestation terminology. This terminology is sort of defined in RFC. It's like an informational, so it's not very much a standard, and I'll get back to like why it's not really a standard later. But these are the terms that you're going to see every time you hear someone talk about remote attestation or there's some project on remote attestation. So if we translate the entire thing from traveling earlier, there is now an organization, which we call the relying party, that needs to make a trust assessment on some sort of computing power that it doesn't know and doesn't have any proof or evidence on, which we call the attester. And then there's a third party which does have access to, which does have information on the attester and on the device that you want information on, and it can verify and certify that that information is valid. So then if we look again at our passport model, we can now translate that into more computer sciencey terms according to like the specification of remote attestation, in which we have the attester, which is the one that needs to provide evidence, who provides the evidence to a verifier, and that verifier then sort of turns that into a signed report where it says, yes, me, the verifier, can actually prove that this evidence is true and that is valid. With that attestation report, you can then go to a relying party who can now trust the attester if they trust the verifier. Now, it gets slightly more complicated because, like I said, it's not a standard. The RFC is like informational. All the terminologies that are in there are sort of the de facto standard, but there's many variations on it. I just discussed like the one in the top left, which is the passport model. But there's also what we call the background model on the left, on the bottom, and then on the right, there's sort of a hybrid between all of those. And if you look at like specific implementations of remote attestation procedures, you're going to see that they always just take all of these little components and they'll just toss them in whichever way works best for their use case and their application. But I would like to cover like the difference between the main ones. So I've talked about the passport model just now, but sort of the second important one that I frequently use in like, edge research is the background model. So the passport model, what's the main advantage? Is sort of it's privacy preserving. Evidence can often be personally identifiable information. If it is someone's actual computer that someone is using that you're collecting evidence on, it can easily be used to fingerprint that device and track it, which is not always allowed. And by having a third-party verifier, that is the one who receives the evidence and not the actual relying party, thus kind of preserving the privacy for the attester. Now, negatives is that it requires more infrastructure, right? It's a lot more complex to set up. You need a separate verifier and a separate relying party, and they somehow need to trust each other. So that can be a bit more complex. So what you can use is the background model, and that's usually sort of if the evidence already belongs to you. Often with like edge devices, for example, what I work with, you have a device that is yours, you just put it somewhere else. But I can see anything that happens on the device because it is my device, it's my compute that runs on it. So there's no like personally identifiable information. Main advantage is that you can sort of merge the verifier and the relying party into one. There's some implementations that really just turn this into a single application. But if you think about like cloud native stuff, this can easily just be two pods running in the same Kubernetes cluster, making it like a lot easier to set up. So those two are like the main important ones that are usually in some way used in these remote attestation procedures. Now, there's a few steps. We can sort of translate this entire thing in three major steps. First one is collect the evidence. The second one is evaluate the evidence. And then the third one is make a trust decision. And this is where the questions that I introduced earlier come back. And the questions I'm going to repeat throughout this talk and that I find very important for sort of setting up a remote attestation procedure. So what do you measure? What are your references? And then how do you make a decision based on those two? And I'm going to try and apply these questions to TPMs and trusted execution environments using Intel SGX. But before I do that, I want to quickly highlight sort of evidence. Evidence can be very broad depending on like what you're trying to remotely test. If you're using a TPM, you're going to have different evidence than if you're using a trusted execution environment. But there's sort of a few things you need to be mindful of that your evidence should always have. First thing is like authenticity. That's usually done by some sort of signature that proves that the data was generated in a cryptographically secure source or stored there. What you don't want is that your evidence is just stored on disk because, you know, an adversary can just change whatever is on disk. So you need that. Authentication, making sure that if you talk to a remote device, make sure that it actually matches the identity that you expect. For example, with a TPM, it's not because the device has a TPM that it is your device with your TPM. So you always need to verify that. And then the major one that's also pretty like straightforward is integrity, right? It needs to be, the data that's in there needs to be valid. Also, as it is transmitted from the attester to whatever other parties that are involved. And then finally, freshness. You're always going to have some sort of nonce in there to make sure that an adversary is not just repeating cryptographic material. So what does that usually results in sort of a multi-step operation, which can get quite complex, in which you need to verify all these signatures and do something with a nonce and all of that. So yeah, this is what you need when you do anything with evidence. Now, I would like to continue with remote attestation in practice. And the main thing is that in practice, it's going to be very diverse. Like I said, depending on what your goal is, your evidence is going to be wildly different, or the architecture, even on how you verify that evidence and all that stuff, can vary wildly depending on the implementation. Now, what I do think is important is the terminologies and the flows that I highlighted before. Those are always going to come back. Anytime you talk about remote attestation, you're going to have your attester, your verifier, your relying party, your attestation report, your evidence, all of those. So yeah, in the next part of this presentation, I'm going to discuss remote attestation in the context of both the TPM and a trusted execution environment, and try to answer sort of those three questions that I stated earlier. Okay, TPMs. General introduction, I feel like most people will know what a TPM is, or at least heard about it and sort of kind of know what it does, since if you have like a Windows laptop, you have TPM. Good things about it is that it has sort of limited functionality, right? It does a few things and it does them really, really well, making them highly secure. They're present in most computers. If you have, like I said, if you have a laptop running Windows 11, you're going to have a TPM. It's also present on servers. On top of that, it's a very cheap device. So if you are building some sort of hardware solution from the ground up, this will not cost you a whole lot of money to put that in there and make your device capable of sort of remote attestation. A few negatives of this. I find the specification quite complex. It's like a few thousand pages. While it doesn't do a whole lot, there are a whole lot of processes to make sure that it does them right. So it can get very complex to sort of work with it on a low level. And on top of that, there's going to be a very large trusted computing base, meaning you need to measure a lot when you're using a TPM for remote attestation. You basically need to measure the entire system. If you compare that to sort of a trusted execution environment, there it is a lot smaller. So yeah, TPM in general. Now we're going to start with our questions, right? The first question is, what evidence do you collect? And to explain what evidence we're going to collect, I sort of first need to explain the technical part of the TPM and how it stores that, how it can cryptographically, in a cryptographically secure way, store information. Now, it does that using a thing called platform configuration registers, and it has usually like 23, 24 of those. And the general idea is it only supports two operations. So you can't just write random stuff to it. It only supports one, the extend operation and a reset operation. And the extend operation will create a new hash based on the old hash that was in there and whatever new data you want to put in there. Basically, it generates sort of a chain of hashes that you can verify later on based on like the final hash that you receive. And the second thing is it can be reset. So you can turn it back to 0, which usually happens at a reboot. Now, there's two major parts to sort of attestation using PCRs and what you're going to measure. The first one is going to be the static part, which is the boot chain, is like what you boot, which is like stored in PCR 0 to 7 if you ever need that. And the dynamic part, which is going to be like what's running on your system, which will be stored in 8 to 15. 16 to 23 are free for if you want an application that can make use of these PCRs, you are free to use those for whatever you want. So I'm going to start off with the static part of what we're going to measure. And we call that a measured boot. This is sort of an image that I made for a paper a few months ago, sort of highlighting the difference between a measured boot and a secure boot. The general idea in a measured boot is that we are going to measure whatever we're going to start. There is a piece of software, usually as deep down and as low level as you possibly can, that will measure the first thing it starts into the PCRs of the TPM. And then every subsequent part of the boot chain will sort of measure the next part, the next part, the next part, until you have the entire boot chain securely logged inside of your TPM. Now, this is different from a secure boot in the way that secure boot isn't super useful in terms of remote attestation, because what will happen if your secure boot fails its security checks, it will just not boot. And then if you have a remote system somewhere in the middle of nowhere, God knows what happens, right? Is there no power, or has it been compromised? You don't know, because it just doesn't boot. So we don't like that for remote attestation. We tend to use a measured boot. So we load everything, the entire static boot system, into the TPM, and we also store it in a plain text log, but I'll get back to that later because you need both to later verify these measurements. An important side note, what is sometimes forgotten about, is that you do need support for this on the lowest levels of your system. With Intel, that's going to be like Intel Trusted Execution Technology, which is a piece of code inside of your CPU that will do this very first measurement. Because if you don't have that and you rely on, for example, a bootloader or even your kernel to be the first measurement, it's very easy to fake those measurements. You really need like a solid root of trust, which we call like the CRTM, the core root of trust for measurement. Mainly important if you like want to develop your own hardware solution, make sure you have this CRTM, make sure you have a piece of immutable or like code that is very strict on what updates it accepts, that can start this measurement process. Second part, which gets a little more difficult, especially when you're trying to verify it, is the dynamic measurements. The idea is that your dynamic measurements build on top of your static measurements. We've basically up to now verified the integrity of the kernel. If we verify the static boot chain, we know that the kernel is intact, and thus we can sort of rely on the kernel security features. And one of those is like Linux IMA, which basically is going to extend anything that you run or any file that you open on your system into the PCR. And again, it's going to log that in a plain text file so we can reference it later. So yeah, those are the two parts, the two major parts that you're going to collect when you're doing attestation on a TPM. Now you have those two parts and you need to sort of be able to transmit them to a verifier for verification. And TPM has some built-in stuff for that, where it basically signs a report over these TPM registers. So you have all the registers, it makes a signature over that to verify the integrity. It signs that with like a special key called the endorsement key. Well, technically it signs it with a key derived from the endorsement key, but you can link that key back. And that endorsement key is certified by the manufacturer to be a valid TPM. So if you look at like the things that we needed for evidence that I described before, this is one of them. Verify that the data actually originates from a valid TPM. So we have our full data collection now. We have a measurement and we have information of the system. And when it comes to TPMs, this is sort of where the difficult part comes in. What are your references? Because you have a bunch of hashes. You have a bunch of hashes of stuff that your system is running, but currently there is no real super good way to find references. The best way to currently do this is to basically fingerprint the entire system and say, this is a good system, and make sort of a predefined list of that. You can combine that with like a list of known good values, saying like this specific firmware and this specific BIOS. I trust that, but it can be very hard to compile that list. And then on top of that, how do you make trust decisions based on that? If you have all these references, it is, again, quite hard to do this in like an elegant way, because it's usually going to be very static, hard to define. It's going to be a black or a white list. These are the accepted ones, and nothing else, meaning that if your software gets updated, and that's especially with the dynamic root of trust, where you measure everything that's running on the system, if one thing is updated or one thing is open that maybe shouldn't have been opened, it will fail that check. So yeah, currently there really is no good way to do this for like highly dynamic systems. This works fine, especially if you only want to like verify the integrity of the kernel, so the static part. But yeah, we need to do a lot more work on sort of figuring out how to verify this. A good start, for example, would be if we could, for example, say in sort of a policy, we don't just want this kernel with this signature, but for example, any kernel that's from like an official canonical source, for example, is good, that is newer than this version. But currently, not really a thing. Still very hard to define all of that. If we look at the specifics of like how you're technically going to make these decisions, I've already mentioned before that we have two things, right? We have the PCR registers, which is basically just one hash per register that you end up with, and we have a boot log. And the idea is that in there, you actually have everything you need to verify the authenticity of all of that information and to verify what is running on the system. So basically what you're going to do is you need to recalculate the entire log and make sure that the PCRs that you end up with actually match what's in the log, what's described in the log. Once you know that that is valid, then you know that the plaintext log you have is also valid. And you can start looking inside the log, for example, for this kernel that I accept and this firmware that I don't accept and all that stuff. And then once you've done that, you also need to do like a bit more to like verify all the stuff for the evidence. You also need to like check the certificate and make sure that it owns the actual EK, the endorsement key, and that it's an actual TPM and it's actually your TPM. So there's quite a few steps involved here, and it requires a very strong understanding of the system that you're trying to measure. This log, like I kind of like shortened it a little, but you can see there's like 142 measurements in, this is just a static boot chain. Each one of those is an impact on your PCR register. So you really need to understand what each of them are in order to verify the boot of a system. On top of that, it can be very hard to debug because you basically only have one hash in the PCR and there's no way of telling what went wrong. For example, when I was working on this, there was a bug in the parser and it never matched. The PCRs would never match just because there's a bug in the parser, but there is no way to debug that because it's very hard to figure out what is wrong in this entire chain. So yeah, it can be extremely complex to do. In short, TPM-based attestation, the evidence is going to be collected in PCR registers and is going to be provided as a signed attestation report. For references, you're going to use the hashes of the system components that you sort of need to fingerprint the system to get all of those hashes. And there's currently no great way to deal with that. Same with the decision, which is going to be very binary now. You're going to define a known good, like a whitelist or a blacklist, and you're going to say this yes and this no. So not super ideal. Now, before I continue on how it's done in trusted execution environments, I do quickly want to highlight abstractions, because like I said, it can get very complicated. You need to check a lot of things. So usually you don't really want to do that yourself. You don't want to interact on like a super low level with the TPM because it gets complex very quickly. There are tools out there. What I like using is Keyline, which basically abstracts your entire TPM to a bunch of APIs, like REST APIs between different components, making it a lot easier for you. It does the whole verifier thing, verification of all the signatures, verifications of all the hashes. It does that for you, and you just provide it with like an acceptable state for a system, and it deals with interactions with the TPM for you. It's open source and it's pretty well maintained, so you can kind of just adjust it to fit your needs. If you needed to do a certain verification of a certain system different for a custom component, you can just add that to it. It's written in Python, so it's not that hard. So yes, use the abstractions. Don't just like try it on a low level with a TPM unless you need like something super, super specific. Okay, we've had the TPM attestations, like how do you do it in the TPMs? Now I would like to talk a little bit about the second part, the trusted execution environments. Quick introduction into SGX. Maybe quick side note, attestation in TDX is very similar, but since TDX is still very new and I have no experience with that at all, I'm just gonna like leave that out for now, and we're gonna mainly focus on SGX in this case. So the general idea, for those of you who don't know, trusted execution environment, the idea is to shield whatever you're doing from the underlying system and prevent like the kernel, a compromised kernel, or your operating system or whatever hypervisor may be from doing anything to your computation. Nice thing is that it is enforced on the CPU level, which makes it pretty secure. You know, your CPU would have to be compromised for it to not work. Pretty small trusted computing base, right? If you look at the TPMs, we had to measure the entire system, the entire boot chain, the entire system that's running. That's not the case here. If you know that your CPU and like the microcode of your CPU and all of that is intact, you can know that your enclave or your trusted execution environment will be intact. You know, a few negatives. It's very expensive. It used to be sort of a different paradigm with SGX. SGX used to be used on like personal devices, you know, the Intel Core i5, i7, i9s. But Intel is really making the shift from these personal devices that run like super small applications to the massive scale cloud data center trusted execution environments. So currently, if you want to buy a new CPU, SGX is only available on like third generation Xeons and newer, which gets really expensive. Maybe one thing, it's also available on a Xeon D, which is like a low powered edge device, but they are also super expensive. So, you know, it's quite a bit of a negative. Another negative is that if you want to work with like what I call like vanilla SGX without any abstractions or without anything on top of it, it can be very complex to work with. There's like this entire document, like an entire book basically on how to develop applications for SGX. Because in vanilla SGX, you can't just take your application, put it in an enclave and have it run. Basically, the standard programming architecture is that you have some small piece of code running in your trusted execution environment that then has like a bigger companion app in the normal world and sort of very strictly defined communications in between, which is sort of what you see here. But that's all changing, and I'll come back on that later at the end when I talk about abstractions within SGX. Now, you might be wondering like, okay, cool, the system is secure, it runs my code in an isolated way. Why would I need remote attestation for this? The main reason you need it is to set up a communication channel to your trusted execution environment. In general, trusted execution environments are not set up with secrets in place because that would make it insecure because your secret could leak like in transit. So in general, the way trusted execution environments work right now is that you, organization A, are going to develop some application that you want to run inside the trusted execution environment. It will usually run on someone else's premises, which in this case is organization B, and it will contain some secrets or some encrypted data that you need a decryption key for. Now, you need to verify that when you send your secret to the enclave, that it actually follows the green path over here, and that it actually gets to your trusted execution environment and is in no way intercepted by the organization you're sending the data to. So the main thing here on attestation is verifying that your connection terminates in a trusted execution environment that has the integrity, that is a real enclave before you send the secrets in there. A quick side note is that there's like a move now to combine all of that. So basically, what happens now is that you're going to combine the remote attestation process in SGX with the negotiation of like a TLS connection. And you can then use that to more securely verify and guarantee that your channel actually terminates inside of the enclave and not outside. And then we get to the attestation details, right? So the 3 questions again. And it tends to be a bit more simple when it comes to SGX, especially the evidence, since Intel sort of neatly defines most of it. And there's 3 major parts. The first part is enclave information. There's these 2 terms called MR signer and MR enclave, but basically it's the signature of the person who created the enclave, who created the code and the data that's inside of the enclave, and then 2, a hash over the actual data and the code and the initial state of whatever enclave you're running. Basically used to sort of uniquely identify that, yes, the enclave that I'm trying to communicate with is actually my enclave and not some other enclave. Second one is platform information, which sort of verifies the integrity of the platform that it's running on. Intel defines these like security version numbers for everything. So your CPU will have a security version number. Your microcode will have a security version number. And a lot of other things that sort of define the security state of the system. And then finally, there's going to be a quote by a separate enclave. The details of that are not super important right now, but it's going to be signed using a provisioning key, and sort of similar to a TPM, that key can be verified to only be able to be used by a valid enclave. So the goal here again is to verify the integrity and the identity of the enclave using all of this information that you collect. Now, like I said, it's a lot simpler when it comes to Intel, because Intel defines stuff a little better, and it's more like suited to like one singular purpose rather than a TPM, which can be used for a lot of different things. So the references are also a lot simpler. The enclave information, yeah, it's just a list of known good values again here, but it's just 2 values that you need to know. You need to know the identity of the person who made the enclave, which is usually going to be you. And you need to know the signature of the actual enclave, which is also going to be made by you in most cases. So you have all that information already. It's not that hard. And then the platform information, the SVNs, those security numbers, it's basically just a version. You're going to have vulnerabilities in certain versions, so you just need to check, are the versions newer than the versions that have security vulnerabilities? If the answer is yes, great, your Intel enclave has integrity. If it's not the case, then you know that you can't use it. And then finally, the signature is also pretty easy to verify, because it has a direct sort of certificate chain to an Intel root certificate, verifying that this is in fact the key that Intel put into a valid Intel CPU at manufacture time. Yeah, and then I've actually already kind of covered this when I talked in the last slide, how you're going to verify this. So verify the enclave, verify the author, make sure that the SVNs are of a higher, newer version than any vulnerabilities, and verify the signature, which can be done in like 2 ways. If you want to like experiment with it and test with it, I recommend that you just use like the Intel Attestation service, which is basically a service that Intel provides that you can send your code to, and Intel will say yes or no. Intel will do the verification for you. Now, this is nice if you have like small deployments that don't have any like requirements in like latency or uptime. But if you do have that, you probably want to set like a decap cache. You want to set that up, which is like data center attestation primitives, and that allows you to sort of do the local verification by like locally verifying Intel's like cryptographic material. So yeah, short summary again on Intel attestation, quotes over your SVNs, the hashes, and all of the metadata. That code is made by the CPU. For references, those are mostly just provided by Intel, by like security notices of Intel, except for the identity of the enclave and the author, which you should usually just have and know. And the decision is basically just like match the values and make sure that the enclave is actually a valid enclave created by Intel. Now I talked about how it can get very, I talked about how it can get very complex to sort of design software for SGX. And then you need like this very specific programming paradigm. But there is sort of a shift. It used to be that an Intel SGX enclave was like, had like 0.5 gigabyte of memory that it could use, which was very limited. And that was sort of the point, that it was like a small little companion app running in a trusted execution environment. But that is shifting now with the new like scalable Xeons that can have 512 gigabytes of enclave memory. There is basically no limit anymore. So as SGX and the whole Intel trusted execution environment matures, there's software and abstractions that are developed around this. Usually it's called like a library OS. I like Grameen because it's open source, it's well maintained, but there's also like a few other ones, and there's some proprietary ones. And the basic idea is that it sort of really simplifies the development. Instead of having to make this secure world application, this normal world application, and have them communicate over some complex calls and stuff, you could literally just take whatever application you have, run it through a tool that Grameen provides, and you can now just run it in its entirety inside of an enclave. So basically, it's a library OS that sort of abstracts away all the difficulties of the trusted execution environment. You can sort of kind of see it as a kernel that's running inside of your trusted execution environment that will translate all of it to something that can run on your CPU. Also, attestations are a lot easier here. In like vanilla SGX, you would have to make a bunch of system calls, do everything manually, but they basically provide sort of pseudo file system that you can just write data to and receive data from, making it a lot easier to do attestations. Yeah, so again, if you can use these abstractions, unless you need like some kind of super specific use case that doesn't work with this, but please use stuff like this and don't go like doing it on a super low level. Sort of a quick thing that I still want to hit on, because I do think it's nice for the future, especially when it comes to like edge computing, but I think is not quite there yet, is ARM Trust Zone, which is basically ARM's trusted execution environment. Few advantages here is that the devices tend to be cheap. Raspberry Pis, you can buy a bunch of them for not a whole lot of money. But currently there are a few like useful implementations of remote attestation for ARM Trust Zone outside of like research papers. And on top of that, people tend to think like, oh yeah, I can just buy myself a little Raspberry Pi, which supports Trust Zone, and just use that and be fine, which is not the case. Not all ARM devices are made equally. Most of them are pretty terrible when it comes to like confidential computing and trusted computing. Because while they do support the like trust zone instructions on the CPU, they don't have everything else that needs to come with it. But is it like secure number generation? They don't have encrypted memory, all of that. So you need to be really careful with what device you pick to run ARM Trust Zone. I'm just gonna hit on this real quick because like it's really not there yet, but I'm hopeful for the future. On how we could do remote attestation and how it's sometimes done in research. The general idea of how most of these devices work is that they have the ability to store some sort of public key in what we call one-time programmable fuses. So basically, you burn a key into the system, and the system will only boot anything that is signed with the private key equivalent of that public key. So basically, secure boot. And I've already talked about it earlier, that I honestly do not like secure boot. I don't think it's a good idea in remote attestation, but in this case, we have to do it anyways. The general idea how you can work then is you can sort of put an encrypted, you can put sort of a key inside of the image for the trusted execution environment that is only decrypted once it's like inside of a valid trusted execution environment. And you then know if you receive data that is, for example, signed with that key, then you know that it is valid information coming from an actual trusted execution environment. So you can sort of measure the real world from your trusted execution environment and provide attestation reports in that way. But still, like, this is all like still mainly in research papers, and I don't believe there's like currently a whole lot of like practical implementations of this. So yeah, quickly want to touch on like why I currently don't like it. I would love to use it, but I don't like it. The OTPs are like honestly terrible in terms of like e-waste. You can burn like a few keys in there. It's not like it's one key and you're done. You can burn in a key and then revoke the key and burn in a new key. But there's a limit. You're not going to put like 20 keys in there. So at some point, these devices are just e-waste because they're just bricked. They're not going to boot anything anymore if your keys are compromised. Second part, secure boot puts the trust decision with the attester, which if you remember the schema of the of remote attestation in general, that is not what we want. We want the verifier to be able to make this trust decision and not the attester. The attester should always boot. It should just tell the verifier what it booted with so we can make a decision based on that. And then finally, it is hard to find capable hardware. Like I said, most ARM devices you're going to find will be capable of executing the trust zone instructions, but will not do it in a secure way. So I am hopeful for the future. I would really love to use stuff like this, but it is not quite there yet. So I've covered basically the things that I wanted to cover. I quickly still want to hit on research that I want to work on and that I feel like is needed for especially TPM-based attestations, is to build sort of a system with more nuance. Like I said, TPM attestations are very hard to verify. It's usually a blacklist or a whitelist that is super, super specific. So we need some sort of system with, like I say here, dynamic collections of known good values. Like I said before, for example, any kernel that comes from Canonical with a newer version, or any kernel that comes from there, or any firmware that is from Dell and newer than this version we want to use. And I would love to extend this with software bills of materials, where basically a lot of regulatory bodies are now forcing companies to make these software bills of materials. So they are more prevalent, we have more of them, and there's a lot of useful information in there. If we look at TPM-based attestation, what we have to go on is basically a hash. And we could correlate that hash to a hash that's inside a software bill of materials and get a lot more information from that single hash using its software bill of materials. And then we can start defining policies, for example. We can say, instead of just having to say this hash, this list of hashes is good for us, we can say, we don't care about the hashes. We just want to look at the software bill of materials. And if there's no like known CVEs, no known vulnerabilities, and it is from like maybe authors that we like to trust, we can boot this and we consider it trusted. So yeah, the goal for the future here is to make it a lot easier to define trust and make it a lot less of a burden on like developers and maintainers of these systems. So I've reached the end. I'm like well within my time limits, I think. Some key takeaways that I want you to remember of this presentation. There is no standard, but the informational RFC is sort of the de facto standard. If you want to have communications and want to talk about remote attestation, you're going to need to know those terms. So you might want to read that thing. It's not super long. There's no real turnkey solution for defining trust. You really need to take those 3 questions that I posed and answer them for your specific use case to decide how you want to implement it. Abstractions, use them. It can get very, very complicated to do it all like manually and by hand. It's sort of similar with like SSL libraries. You're not going to like do all of the cryptographic stuff yourself. You're just going to use a library. It's the same with attestations. If you don't want to invest like a ridiculous amount of time and money in it, use these abstractions, use these open source abstractions and sort of adjust them to what you need. And then finally, we are working on making it a lot easier. But yeah, we're not quite there yet for some systems, and make it a habit to try and remotely test any remote systems. If you put a system anywhere outside of like your trusted boundaries, you will need to do remote attestation on it. So this is the end of my my webinar here, and we have some time for questions now. If you think of a question later, my email address is like right there, so you can just shoot me an email and we can have a conversation there. So thank you.
Yes, thank you, Jordi, for the very interesting presentation. I hope that will help a lot of people. I'm reading a question that we already have in the chat. If you want me to read it out loud, or I don't know if you can see it.
Wait, I'll stop sharing my screen because I don't see the chat currently.
I can read it for you.
No, no, I see it. I have it now.
Okay. So just to read it for everyone.
Yeah. There's a lot of information in the question. How would you be able to scale them? The thing is that with you can pretty easily scale all of like the verification components. I don't know if that sort of answers the question, but for example, when I look at the abstractions for TPMs, the Qlime software is sort of built to be scalable. It's built to be deployed on, for example, a Kubernetes cluster. So you can just have multiple verifiers working together to handle all of that attestation stuff. So I don't know if that fully answers the question.
You can also take it offline since you gave your email. So if there are further questions, feel free to reach out directly to Jordi or to us. Verlaine, you also have a question?
Yeah, so maybe first just a note on the previous question. Jordi already touched on it a little bit, but I think scaling to many systems, to thousands, 100,000s, millions of devices, it's not necessarily a technical limitation. It's more of a process limitation, because with the current system, from the moment some of these devices deviate from each other, have slightly different operating systems, have slightly different hardwares, the measurements are going to deviate significantly. Basically, their measurements are going to be completely different. And so you need to have a good process in place in order to ensure that for every device, right now, you know what the expected measurements are and which measurements to trust. This is something specifically that we are trying to solve by connecting this with software bill of materials, where our goal is to write basically a policy verifier, or like an attestation verifier, that not only looks at the hashes, but also connects these hashes to, okay, what does this actually mean for software versions that are running on this, for types of hardware that are running on this, and then can be able to connect it to CVEs and things like that, so that basically the system for you can define what level of trust it's connected to which attestation. And that will make it a lot easier to scale this to very heterogeneous fleet of devices, because instead of having to define for every single device firmware combination, having to define what trust means for that combination, you can simply write general rules of like, okay, I want a kernel version higher than this, I want hardware version higher than this, or hardware versions below this are not trusted anymore, or are only semi-trusted.
Yeah, we very much need like more of a policy rather than these like black and white lists that I described. Because right now, indeed, if you have thousands of different systems, you're going to need thousands of different white and black lists that need to be maintained for each one of those like systems. So yes, we're sort of trying to move towards more of like a policy-based thing where we can just define, like I said, any kernel newer than this version made by a trusted entity is fine, or anything that there's no known security vulnerabilities is fine. The move to sort of policy definitions for that will really enable like a lot more scalability. Because indeed, like you said, it's not really a technical, it's having to deal with all of that verification information.
And then another question for
maybe
you.
before we go through another question, but then sorry to jump in to maybe complete what I was rereading the question. Do you think there's a scale in terms of level of security based on the different categories, as in TPMs, PUFs, certification? Is there something more secure or less secure?
It very much depends on what your use case is. Like I said, remote attestation, the way you can do it varies widely depending on your use case. If you can use like a trusted execution environment, those tend to be a lot easier to secure, but they are also used for a very specific purpose. If you want to provide remote attestation in a more general way, sorry, I lost my train of thought here again. Can you do the question again?
To complete the question before, probably part of it was to have an understanding if there's a different level of security in terms of the different solutions here. As in, is there something that is
Yes.
considered more secure but more expensive, for example, so that companies can
Yes.
also evaluate
So yeah,
based on cost?
I guess I kind of answered that with yes, a trusted execution environment tends to be more secure, but it tends to be for a very specific purpose. And a TPM often tends to be harder to really make it airtight and secure, but it is more general purpose and you can use it for a lot more things.
Thank you.
My question is in a similar line, like more or less, like what is the landscape currently in terms of vulnerabilities of this hardware? Do we see a lot of vulnerabilities in these hardware roots of trusts in these enclaves? And will will some of these be solved in the future? Can some of these problems be solved by software updates, or do you need to buy new hardware? What does that look like?
As far as I'm aware, on like the Intel side of things, there are no like breaking hardware issues. I know that there are some like Russian researchers that published some stuff, I think a few weeks ago, on possibly extracting sort of root keys from the CPUs, but like Intel then responded to that from, yeah, you're doing this on a CPU with like microcode from 2017, you know, that hasn't been updated since then. So yes, if you run old hardware, there might be the possibility of vulnerabilities. But I think Intel, especially when you consider these large companies, Intel is pretty on top of that. If something like that is discovered, Intel will publish that and usually patch it pretty quickly. But as far as I know, there's like no like super breaking like actual hardware issues that can't be patched in like Intel stuff.
Okay, and then another question. Let's say that somebody watching this wants to start using this not on devices but in the cloud. Like, is there a place we can point them to start experimenting with this? Are there cloud providers that provide this functionality?
Well, when you talk in terms of TPMs, I don't think so. I'm currently not aware of any, but stuff like trusted execution environments definitely. I'm not sure about TrustZone. I know that there's some cloud providers providing ARM servers now, but I'm not sure if they like enable TrustZone on that. But like SGX definitely. Most of the major cloud providers have some sort of SGX enclaves that you can just run your workloads in. I don't have any experience using those myself, but I know that they exist and they are out there.
Okay, thank you both, Jordi for the answers and Merlin for the questions. I don't know if your cat has any other question. Very briefly.
Cat is talking a lot, but I sadly can't speak Cat, so I have no idea what his thoughts are on it.
Very briefly, I would like to remind some of the upcoming activities that will happen between October and November. So tomorrow we have, still for Opencloudification, an in-person event at the Beacon, one of our partners in Antwerp. It would be a lunch and learn. On our website, you can still find the event. You can register and participate. 20th of November, there will be a track specifically on the state of the cloud. Merlin will be our speaker there. We will provide more information on the location soon. And 26th of November, there's a workshop dedicated to software bill of materials, so something that we also briefly touched today, and it will be handled by our partners at UGANT and IMEC. With this, I think I can thank you for, well, you, Jordi, for presenting today, and our public to attend. And I think I'll invite you to the next event. Thank you so much.
Thank you.